Example 8. Simplifying expressions of the form cos of theta minus I sine theta all to the power of n. So our question here is simplify the cos of pi over 3 minus I sine pi over 3 all to the power of 6. So at this point you might be thinking, oh, we can go and apply de Moivre's theorem straight away, but actually because there's a minus here, we're going to need to do a little bit of work. So note the polar form will be the cos of the argument plus I sine of the argument. So it's always going to be a plus, and that will never change. So there's a few ways where we can approach this question. And I'm going to start off by looking at what this means. So we're going to use a unit circle. And with our unit circle, we've quadrant 1, 2, 3, and 4. And then whatever way you use to remember what is positive in each quadrant. So cos is positive, all are positive, sine is positive, and tan is positive. So in this scenario here, cos is positive, but sine is negative. So we're wondering which quadrant does this sit in? And that will sit down here in the fourth quadrant. It is given us then an acute angle pi over 3. So what we are being given is this angle here, which we can call A, which will be the reference angle. So that's pi over 3. So that's what they've given us. So to make a true polar form, and I'm going to use positive angles here, we want to understand the argument moving this way. So this will be theta. So we need to understand the large reflex angle rather than the small reference angle that we've been given here. So if we were looking for the argument, and I'm going to work in radians, but if you need to work in degrees, I'll work alongside of it. So the argument that we're going to have here, if I think in degrees, it would be 360 degrees. Take away this angle, which in degrees is 60 degrees. And that will give us 300. But we're working in radians, so if you've page 13 open in front of you, you can do these conversions quite quickly. 360 degrees, that's 2 pi. Take away the angle which we have, which is pi over 3. And that is 5 pi over 3. And that's what gives us theta, the argument. So this, although not polar form, is giving us a similar form, which would also have an or, so the modulus in front of it. So that will be a 1. So we don't have to worry about that. That won't change. So if we think then in polar form, it's simply going to be cos of 5 pi over 3 plus I sine 5 pi over 3. You could also use negative angles here if that's the way you'd like to go. So now that I have this in polar form, what we can do is we can use de Moivre's theorem to convert cos of 5 pi over 3 plus I sine 5 pi over 3 all to the power of 6 into something just a little bit more manageable. De Moivre's de Moivre's theorem, which is found on page 20 of your log tables, tells us to simply multiply the angle by the power. And that's also coming from our shortcut of multiplying complex numbers when they're in polar form. So that's 6 times 5 pi over 3. And when we work that through, that gives us, so we get a little bit of cancelling here, so that's a 2 and a 2. The angles should always match, so this will always tell you if you're on the right track. So I have cos of 10 pi plus I sine of 10 pi. Now remember that we will be looking at this point to understand, is theta, our angle, less than 2 pi? Because if it's 2 pi or bigger, we will have we'll have to take away one of our rotations to bring it back to an angle between 0 and 360 degrees, or 0 and 2 pi if we're talking in radians. So in this case, 10 pi is most definitely over 2 pi. It's a number of rotations. I'm pointing this out here just so you remember to check your question and the answer before you present it. But I'm going to go back to the question we've actually been asked, and we've been asked for the answer in rectangular form. So actually it won't make a difference for us because we're not going to leave it in this form. So if you would like, you can convert that. If you want to convert that, that is a multiple of 2 pi, so that means it will be equivalent to 2 pi, and that means 10 pi is actually the same as 0. So cos 0 plus I sine 0, and you can work it that way. Alternatively, what you can do is you can go to your calculator, make sure it's in radian mode, and type in cos of 10 pi, and we should get 1 plus I sine 10 pi, and that's I times 0, and that basically gives us our final answer of 1 plus 0i. If you're asked for rectangular form, I would include both the real part and the imaginary part, even if that imaginary or real part is 0. Example 9. So using de Moivre's theorem, and this is a very unusual little question. It appeared as part of our syllabus, so it's actually outlined in the syllabus itself as an example. This question itself has come from a mock paper, so it is a little bit more complex than maybe other things we've seen, but it's a nice example, especially given that the department have specifically said, here is an example. So it gives us a big hint by saying use de Moivre's theorem to prove, and we have this really quite bizarre looking thing because de Moivre's theorem at this point we should know is all about complex numbers and expanding complex numbers to a given power, and there's no complex numbers here. So given that we have some thetas here and so on, we're going to start with the complex number cos of theta plus I sine theta. So I'm going to start with that. That seems like a good place to start. And we have power 3 and some 3's in here. So I'm thinking that actually we probably need to put a power 3 here if we're talking about de Moivre. So we're going to have a power of some sort. Power 3 seems like it's the right way to go. And what we're going to do is we're actually going to expand this in 2 different ways. The first way is I'm going to use de Moivre's theorem. So I'm going to come along and say that's the same of cos of 3 pi, cos of 3 theta plus I sine of 3 theta. Very straightforward. So this is using de Moivre. The second way we're going to do is you can use either binomial expansion or you can multiply it out the long way. I'm going to use a binomial expansion. And binomial expansion is actually on the same page as de Moivre's theorem, which is page 20 in your log tables. So we're going to do exactly the same sum, but just in a different way. So the cos of theta plus I sine theta, and we're going to do to the power of 3. So the expansion is n choose 0, so that's 3 choose 0, and it's going to be the first term, cos of theta, all to the power of n, so that's cos cubed theta, plus 3 choose 1, and then that's going to be cos squared theta multiplied by I sine theta, plus 3 choose 2 cos theta, and it's going to be I sine theta all squared, so just make sure that I is squared as well. And the final term, so remember there was always one extra term, so power 3 we have 4 terms, power 5 there'll be 6 terms, and so on. And we know that this binomial expansion is something we do a lot because the shortcut for squaring that you might do in your head, square the first, twice the first by the second, and then square the last, it's coming from this binomial expansion. So the last piece is 3 choose 3, that's how I know I've got to the end. I can't go further than that, and it gives an I sine theta all to the power of 3. So I'm going to tidy this up. So 3 choose 0 is 1, and that's just cos cubed theta. 3 choose 1 is 3, and that I'm going to just pull out the I in front so it doesn't get lost. And then we have cos squared theta sine theta. 3 choose 2 is also 3. We then have I squared. I'm going to pull the I squared just out the front, just so it doesn't get lost. It doesn't matter where it goes, it's all multiplication. So then that's cos theta sine squared theta. And the last piece, plus 3 choose 3 is 1. And we get I cubed sine cubed theta. So I'm going to come along now and focus in on the i's to a power. So we should know at this point that I to a power bigger than 1 should never be written. It should be converted. So I'm going to tidy this up a little bit more. So cos cube theta plus, I'll leave the I out here, 3 cos squared theta sine theta. We should know that I squared is minus 1, so that's minus 3 cos theta sine squared theta. And then I cubed is actually minus I, so we get minus I sine cubed theta. Now what we have is we have cos theta plus I sine theta to the power of 3, and we've expanded it in 2 different ways. With these kind of questions, when you've done anything, it's good to stop and look at what do you have and what do you want. So notice that we have, grab my highlighter, so up here we have sine of 3 theta, and I'm looking around, do I have that? And I do. I have that here. And then we're looking at 3 sine of theta. I don't have that, but sine, well, I have 4 sine cube theta. I don't have a 4, but I do have sine cube theta. So what I'm actually going to do is I'm going to say, well, I've expanded in 2 different ways, but effectively my answer should be the same. So therefore, the imaginary parts in both of my expansions, so de Moivre's and binomial, they should be equal. Notice I even have that minus in front of the sine cube theta. So I'm going to say that the yellow in the first equation should be equal to the yellow in the second equation. So what that's going to look like, I'm basically going to say I sine 3 theta should equal I 3 cos squared theta sine theta minus I sine cubed theta. And then I'm going to cancel off those i's or ignore the i's, whatever way you want to think of it. And now I'm very, very close to getting, I'm very, very close to having the equation that they want me to prove. So this is good. I'm going to change colour. So this is good. That's fine. I think I'm happy with this as well. But really my focus is going to be on this part here and breaking it up into something a little bit more useful. I'm thinking from what's above, I'm going to try break it into a sine and then a sine cubed in some way, so we can work with it. So let's clear the screen and move on. Okay, so we're focusing in on that 3 cos squared theta sine theta. I'm happy with the other 2 pieces, so I'm just going to rewrite this a little bit clearer. So I have sine of 3 theta is equal to 3 cos squared theta sine of theta minus sine cubed theta. We're focusing in and looking above and thinking, well, I currently have 3 cos squared theta sine theta, and up here I have a 3 sine theta. So is there something that we could replace this cos squared theta with? And if we go to the log tables on page 13, we have this little formula here. And this little formula isn't helpful straight away, but actually if we rearrange it, we can get a little formula that says the cos squared of an angle is 1 minus sine squared of an angle. And this, as a substitution, will help us with the right hand side. So I'm going to replace this with 1 minus sine squared theta times sine of theta minus sine cubed theta, and we get 3 s sine theta. So just be careful multiplying 3 by the whole bracket by sine theta. You can do 3 sine theta if you prefer to move it in front of it. So I'm doing 3 by 1 by sine theta, and 3 by minus sine squared theta by sine theta. So that's minus 3 sine cubed theta minus sine cubed theta. And then we can add our like terms, which are these two pieces here. So that is 3 sine theta minus 4 sine cubed theta, and the left hand side has been the same, we haven't touched it, and that is exactly what they wanted us to show. So the next thing we're going to look at is the general form of the general polar form of a complex number. So we've seen the polar form of a complex number, and now we're going to generalize it. And this is very much linked to the general solution that you would have done in trigonometry. So we're going to use the same method. So when we're using de Moivre's theorem to find the roots of a complex number, we're going to use this general polar form. And what this allows us to do is basically find more than just the single answer. So we would have seen this general solution when we were solving, looking for the angle in trigonometry, and we could find all the possible angles with that solution. So this is very much linked to what we've already done, and we're basically going to be adding in a rotation, and that rotation is 360 degrees or 2 pi. So this is what we end up with. It looks very, very similar to the polar form. The only difference is our 2n pi added on. That could also be n times 360 if we're working in degrees. So this is the add-on. This is my rotation, and it's the general rotation. So if I add on 2 pi, I rotate it. 2n pi is any number of rotations. So we would then sub in n is 0, and n is 1, and n is 2, and continue until we would have all the roots of the complex number. This idea of roots of the complex number, we're going to explore it in the next example. So looking for the nth root of a complex number. So they're asking us here to solve this equation. So in the very first instance, what we would tend to do is if I had z cubed equals 8i, we would work backwards and simply say, well then z is the cubed root of 8i. Now that's fine if 8i wasn't 8i and if that could go into the calculator, but that can't go into the calculator. So instead the way we would write that is 8i to the power of a third. So remember that the cubed root is the power of a third, square root, power of a half, and so on. So that is what we basically end up with. Z is 8i to the power of a third. So what we have now is a complex number to a power. So this is a great place where we could apply de Moivre. So what we're going to do is we're going to take our 8i and we're going to change this to polar form, and more specifically than polar form, general polar form. Because if we can change that to general polar form, it allows us to get all the possible answers. And if we have z cubed, we will have 3 answers. If that was z to the power of 5, there will be 5 answers, and so on. So first step, we are going to get general polar form, and then we're going to apply de Moivre's theorem. So let's follow our steps. First step, sketch. So we're going to sketch this out. Always sketch it out. So we have 8i. 8i is going to lie somewhere. Oh, apologies. Gone along the wrong axis. Go again. So 8i is going to sit up along here to this point here. Now, although you might be thrown, this actually makes your life much easier, because you should know that if that's the argument theta, that theta is actually just 90 degrees. We're going to work in radians, so that means pi over 2. And the modulus is going to just be 8, because you don't even need to use your formula, your a squared plus b squared under the square root, because it's vertical. So any vertical or horizontal complex numbers are super easy to work with. So that means polar form would be 8 cos of pi over 2 plus I sine pi over 2. And that would be polar form. But I want to go one step further and get general polar form. So that means putting in those rotations. And we're going to put in some number of rotation we don't know. So we're going to have pi over 2, and I'm going to put this in another color so we can see it, plus 2n pi plus I sine pi over 2 plus 2n pi. Okay. So that is our general form of z cubed. And now we're going to work backwards like we have done. So we're going to come along and we're going to say that, well, then z is equal to 8 cos of pi over 2 plus 2n pi plus I sine pi over 2 plus 2n pi, and that's all going to be, I think I'm missing a bracket here, so close my bracket, square bracket, and that's all going to be to the power of a third. And this is where we can apply de Moivre's theorem. So we're going to have 8 to the power of a third. So if you need help with that, page 20 of your log tables. So cos of, I actually usually do this in a different color, so I'll keep that up so we can see it. So you're applying a third as a power on the modulus, and then you're doing a third of pi over 2 plus 2n pi plus I sine 1/3 pi over 2 plus 2n pi. And we'll just do a little bit of cleanup to make it a bit easier. That's the cubed root of 8, so that gives me 2. And we get cos of pi over 6 plus 2n pi over 3. Now you can simplify that into a single fraction, but there's absolutely no need. And both of these angles should always match. Don't just assume though, use it as a chance to double check your work. But that should, they should always match. So now we have an answer for z, but it's in terms of n. So we have, remember we started with z to the power 3, which means there's 3 answers that we want. So we're going to take that general solution and we're going to sub in values for n in order for us to get 3 different answers. So now that I have the general solution, I'm going to get my 3 answers by subbing in the first instance n is equal to 0. So that will give me the answer that z is equal to 2 cos pi over 6 plus I sine pi over 6. But in this case, unless you're specified otherwise, we are going to convert into back into rectangular form, so a plus bi. So if we convert that back into rectangular form, we get root 3 plus I. So that's by putting 2 cos of pi over 6 into your calculator, get root 3, and 2 sine of pi over 6 into your calculator, and you get 1. You can also use page 13 to help you do that. If you're using your calculator, just make sure it's in radian mode. So then the second answer we're going to have is 2 cos of, now we have a little bit of work to do here, pi over 6 plus, it ends up being 2 pi over 3 plus I sine, and the same angle, pi over 6 plus 2 pi over 3. And if we were to clean that up, it ends up being 2 cos, and when we work with this, we get 5 pi over 6 plus I sine 5 pi over 6 and then into the calculator, and we'll be able to work out that's minus root 3 plus I is n equals 1. And the last one we're going to do is n equals 2. So that'll give us our three answers. Well, we always start with n equals 0, so no rotation. So the answer just as is. And we get z equals 2 cos of pi over 6 plus, so this is 2 times 2 times pi. So that's 4 pi over 3 plus I sine pi over 6 plus 4 pi over 3. And cleaning that up, we get 2 cos of this works out as 9 pi over 6 plus I sine, oh, I should actually simplify that. So that's 3 pi over 2. 3 pi over 2, 3 pi over 2. And then into the calculator, and we get 0 minus 2i. So the three roots, sorry, now I'm after going through it. So the three roots of z cubed is equal to 8i are these answers here. Example 11. So we're looking at the nth root of a complex number, and this time it's just a little bit more difficult because we're going to have a little bit more work with the polar form than we did in the last question. So to get polar form, we're going to sketch it out. So my sketch gives me something like this. So minus 2 root 3. There is my reference angle A. Creating my right angle triangle here. Here's my adjacent side. That adjacent side is 2. My opposite side, that's 2 root 3. First thing, oh sorry, no, actually I'll put in here first my theta. That's my arguments. First thing I'm going to work out is my modulus. The modulus is the length or the distance from the center 0, 0. We get that as the length of, and in this case it's actually z squared, and that is the square root of a squared plus b squared, and that works out as 4. And then the second thing we need to do polar form is the argument. So the argument is the angle going from the positive sense of the x-axis. And before I can do that, we're going to need to work out A, the reference angle. So the tan of A, using the triangle we have in our sketch, is opposite over adjacent, which is just going to give us root 3. So that gives us an angle A, pi over 3. And if you're still struggling with your radians, you can kind of keep the degrees running side by side to help you, and that would be 60 degrees. So using page 13 in your log tables to help you as much as possible. And that will help not only with finding out the actual values that we need of the angles, but it'll help you with the radian degree conversion, so keeping that straight in your head. So now I have A, and if we look at the diagram to work out theta, I'm thinking in degrees, and I'm saying it would be 180 plus 60. We are working in radians, so when I come back, I'm talking theta is equal to, instead of 180 degrees, we're talking about pi plus 60 degrees, pi over 3. So that gives us an argument of 4 pi over 3. So that means in polar form we have z squared is equal to 4 cos of 4 pi over 3 plus I sine 4 pi over 3. So we're working backwards. So I want to get z on its own. Usually we talk about the square root, but instead, because I want to use de Moivre's here, I'm going to write it as an indice or a power, and the square root as a power is power of a half. We should be really familiar with that one from all our work in calculus. so power of a half. Now before I actually apply that power of a half, I'm going to need to get two different answers. So how I get those two different answers is I then have to talk about this as the general solution. So I need to understand the general polar form. And to do that, I'm going to actually put in my rotations. So it's going to be cos of, okay, hopefully we won't run out of space. So it's going to be 4 pi over 3 plus 2n pi plus I sine 4 pi over 3 plus 2n pi, and we're still talking about this all to the power of a half. So now that we have our general polar form, we're going to apply de Moivre. It's really important that you apply de Moivre after you have added in that rotation. So it has to be in general polar form first. So we have 4, it's going to be to the power of a half, and then what we're going to get is cos, and it'll be a half times our angle, which is 4 pi over 3 plus 2n pi, so our rotation, plus I sine, and we have a half times 4 pi over 3 plus 2n pi. And that is like a general answer. We're going to clean it up a little bit more. So power of a half, same as square root. So 2 cos, cleaning this up, we get 2 pi over 3 plus n pi. So all I'm doing there is I'm multiplying the half into that bracket. Half times 4 pi over 3 and a half times 2n pi. So we have I sine, and it's 2 pi over 3 plus n pi. So that's just a cleaned up version. So in order to get my two answers, we're going to get n equals 0. So sub in n equals 0. That gives us, keep my z equals 2 bracket cos of 2 pi over 3 plus I sine 2 pi over 3. And you can go to your calculator and do that, and we get minus 1 plus root 3 I. Second answer, we're going to sub in n equals 1. We have a little bit of extra cleanup to do here. So z is equal to 2 cos of, we get 2 pi over 3 plus 1 times pi, so just pi, plus I sine 2 pi over 3 plus pi. I'm going to clean that up just a little bit. So I'm going to get this angle and combine them. So cos of 5 pi over 3 plus I sine 5 pi over 3. And again, that can go into your calculator because we always want to give our answer back in rectangular form, and we get 1 and then minus root 3 I. So our two answers for z are minus 1 plus root 3i and 1 minus root 3i. And you'll notice that, and it's not a coincidence, those numbers and the way that they are, because there's only two different solutions, they effectively mirror each other. So we get that minus 1 plus root 3 and then a plus 1 and a minus root 3. So this is our final example we're going to see, and this is an exam question. So z is equal to minus root 3 plus I, and that's a complex number where I squared is equal to minus 1. First thing they want us to do is to write z in polar form. So first thing we're going to do polar form is we're going to do our sketch. So our sketch is just to give us an idea where this complex number is. So when I go to sketch this, it's minus root 3 plus I, which brings me somewhere over here. The angle I'm then working with, so my reference angle is A, and completing the triangle, I have an adjacent side here, which will be root 3, and an opposite side here, which will be 1. So remember that I is just another way to say 1i. But the angle I actually want is the argument, which is from the positive sense of the x-axis. So it's this one here. So two things in order to write a complex number in polar form. The first thing I need is my modulus. That is the length or the distance from 0, 0. And the formula for this is or. It's written like just like our distance will be with two straight lines. And it's the square root of a squared plus b squared. So basically the real part, so the a squared plus b squared. Note that the I does not go in. So that's the square root 3 plus 1, which is 4, and that gives us an answer of 2. The second thing that we need to know in order to do polar form is our argument. So in order to get the argument, we're going back to what we know about trigonometry and our unit circle. I'm going to work first with the reference angle A. The tan of that is opposite over adjacent. So working that through, we get pi over 6, or if you prefer to kind of keep your head in degrees, that's 30 degrees. So for these kind of questions, you should have page 13 open in front of you, so you can really clearly see that link between degrees and radians. So that is my reference angle, but we're actually looking for the argument. If it's easier, you can look at the argument in degrees. So it would be 180 degrees minus the 30 degrees, which would end up giving us 150 degrees. We want to work in radians, so that would be theta is equal to 180 degrees is pi minus pi over 6, and that gives us theta is equal to 5 pi over 6. This gives us our polar form as z equals to cos of 5 pi over 6 plus I sine 5 pi over 6. If you want to do that in degrees, you could leave it as 150 because it doesn't say anything. I couldn't really penalise you for using the degrees, but it is good practice to work with your radians through any questions you can, because in an exam situation, if you have to use radians, there's no way around it. So the second part is then asks us to use de Moivre's theorem to find z4, z to the power of 4, giving your answer in the form a plus bi. So we have z as a complex number, and now we're going to do z to the power of 4. So from the previous part, we know that z is equal to 2 bracket cos of 5 pi over 6 plus I sine 5 pi over 6. We want to come along and do that to the power of 4. So we're going to take this and go to the power of 4, and we're going to use de Moivre. So z to the power of 4 is equal to 2 to the power of 4. And then we have cos of the power in 4 times 5 pi over 6 plus I sine 4 times 5 pi over 6. So do a little bit of cleanup on this. Z to the power of 4 is equal to, that's 16 cos of, and you can clean this up, that's 10 pi over 3 plus I sine, and again you can clean this up and double check while you're doing that you are that you have the matching argument in both the cos and the sine. Now it's important to note here that actually the angles are bigger than 2 pi, so you don't want theta any bigger than 2 pi, so it should be less than 2 pi. Because we're going to bring it back to rectangular form, it's actually not going to make that much of a difference, but in another question it could. If you prefer using page 13, you might want to bring it back. So if you're using your calculator, you can put this in straight away. So we do, I just tried it out, what we're going to put into the calculator, 16 cos 10 pi over 3, so just multiplying out the bracket, plus I'm going to leave that there, 16 sine 10 pi over 3. So remember, you can't put I into the calculator, so you're doing 16 cos 10 pi over 3, and that gives us minus 8, plus I, and 16 sine 10 pi over 3 gives us 8 root 3, and that I can be put at the end, but generally when we have a square root or a third, we put the I in front. If you wanted to at this point do a little bit of cleanup, you'd take away 2 pi. So 10 pi over 3 minus a rotation, so 2 pi, and that would leave us with 4 pi over 3. So you could work with 4 pi over 3 instead of 10 pi over 3. It would be the same result. If we didn't want it back in rectangular form, if we wanted to give it in a polar form, we would need to take away that rotation to tidy up the angle. So the last part of this is a very interesting piece. It says using the fact that z is one of the roots, or otherwise, so using any other method, find all the other roots of z to the power of 4. So if we want to work out, so basically what we end up with is z to the power of 4 has an answer, and we've worked that out, and that answer is minus 8 minus I 8 root 3. And we could go backwards by doing power of a quarter. Now you'd say, well, we just get back to z. But z would just be one of the roots. Given that there are 4 roots, we would then have to use the general form, the general polar form, apply the power of a quarter and work through it. So just like our previous example. But because it's power of 4, we have a very special little piece. It's a very interesting little thing that happens and that we can utilize as we're going through. So because I know that z is a root, and that is minus 3 plus I, I'm going to use that fact, like they told me in the question, using that fact. I'm not going to use the otherwise. I'm going to use that fact to find the other roots. So what I'm going to do is I'm just going to do a plot. So here is my minus root 3 plus I. So I'm going to just dot that there, and I'm going to call that z. So there's going to be 4 of these, which means that they're going to be equally spaced around a rotation or around 360 degrees, which means they're all going to be 90 degrees apart. And this only happens when there are 4 answers. So when we're looking for basically an answer to the power of a quarter, like in this question, and they're all going to rotate anti-clockwise and at a 90 degree angle, because I'm going to have to fit 4 of them in. So there's my 4 answers. Now that's great, drawing it out, but then how do I get those? So at the very start we would have looked at how graphically we will get this 90 degree anti-clockwise rotation, and to get it we would have taken our z, I'll just go over it, I don't know how dark that is, and we would have multiplied it by I. So this is IZ, this is I squared Z, and this is I cubed Z. So effectively we end up creating a circle that has a radius equal to the length, equal in length to the modulus of Z, and where all of these roots are equally spaced throughout the circle. That will always be true. The roots will always be equally spaced around the circle, but because it is 4 roots, they're going to be equally spaced at 90 degree angles, and we can use that idea of I. I multiplying by I gives us a rotation anti-clockwise. So basically my answer is going to be Z, IZ, and when you work that out we get I times minus root 3 plus I, and that becomes minus 1 minus root 3i. I squared z is just minus 1 times minus root 3 plus I, which is root 3 plus I. Root 3 minus I.